going to give us a talk on Boolean games in a triangle using bipartite and tripartite entanglement.
So first, everyone online, can you hear me well? If at some point you don't hear me well, please just type it in the chat or say something, okay? So yeah, the title is that you're wondering what the background is. So this is the background. I did this drawing for the intercultural project in Heidelberg that I was last September. And this drawing has all of the elements in my research. How can I? Maybe. Well, should be. So the Boolean games represented by the Boolean inputs and outputs, which are those coins that you're seeing over there, so either 0 or 1. And then we will have also Boolean functions that you take from the inputs and the outputs. That's the part of Boolean games. Second part, which is played in a triangle, represented by that Penrose like triangles, if you like. And because they will be playing those games in this triangle configuration, 3 games. Finally, the part of, does anyone know how to, maybe. Is it where? Okay. Hi, okay. Oh, yeah. Thank you. Yeah, thanks. So the part of bipartite and tripartite entanglement, I represented with sandwiches. Bipartite, because we have in that one, we have sandwiches of 2 slices. So that represents bipartite entanglement. And the other tripartite has 3 slices. So each slice would be your qubit or whatever. And I guess now I've ruined sandwiches for you forever, because now you'll always be thinking about entanglement, right? If you don't know what it means, entanglement, here's a short definition. If we have a system with n parts, if we cannot describe the whole system by just describing the individual parts, we say it's entangled. That's our definition of entanglement. And the other is just artistic or nerdy stuff. Particularly proud about this Dalí clock, if you like. That represents also that we are late for climate change and clocks are literally melted. So, yeah. Here, I have explained all of the elements that I represent my research in this drawing. First, I'm a physicist, so we love to explain why we do things and give motivations. The reason that I chose this research is because it's a mix of quantum games, quantum networks, and quantum resources. Here we have a Venn diagram. The part of quantum games would be the part of Boolean games. The part of the quantum networks will be the triangle network, and the part of quantum resources, because I'm comparing 2 types of quantum resources, 2 types of entanglement. Let me give you a brief introduction to quantum games. So a quantum game is a game that you have normal, and then you put quantum resources. Basically, you have your game and you put quantum stuff there, somehow, somewhere.
Sí, perdona. ¿Puedo sentar aquí? Gracias.
One example would be the CHSH game that probably some of you are very tired of me hearing.
A veces de estar, a veces no ve.
About that.
Someone is muted. Pues va enviar el jazz i estem connectats ahí uns quants. Vull dir que estem... Victoria, ella, yo, Masogro, ese no sé qui és, este és de Pinós, este no sé qui és.
Yeah, no, how do I get back to Zoom?
I tal, no sé què, seran amigues seues.
Yeah, perfect.
Sí, va, un ratet, tampoc entenc, vull dir.
They're speaking Spanish, so who's this? Mute all. Okay. Sorry about this, of course. Anyway, so quantum games are just a theoretical tool, but it has many applications, for instance, in quantum cryptography, quantum information, quantum computing, and so on. The part of, if you're interested in knowing a bit more about quantum games, you can check out that review. It's very comprehensive, and it gives you the full flavor of quantum games. The triangle network, it has been widely studied in the terms of quantum non-locality. Lucky for you, I'm not going to explain what non-locality is, but here you have lots of papers that they use this triangle network, very simple, and they focus on studying non-locality. But I haven't seen that with games, so that's what I thought of doing. Yeah, Michael, we were discussing, so maybe we could do that. I could do that. The part of quantum resources is very, very important to study performance for quantum technologies. For instance, for quantum cryptography, quantum information, quantum computing, and I had to add quantum sensing. Damien gave a talk about that. So it's very important to know how these resources perform. The mix between networks and quantum resources, it has been done in Triangle Network. Here you have a few papers that they use the Triangle Networks. We have the nodes over there, and they are distributing bipartite entanglement. So I'm distributing two of each. It's mostly bipartite that has been done. So I thought, why not bipartite? Just keeping the same amount of qubits. The mix between quantum resources and quantum networks is very important because we would like to have in the future a quantum internet. This is a nice picture about the quantum internet. So we'll have nodes over there, and they'll be connected with quantum resources, and it will allow us to do secure communications, sensing, timing, GPS, network quantum computing. Probably you've heard of quantum computers. So it will allow us to exploit the advantages given. I've never seen a quantum computer before. That is one example, is IBM's. And look how Biden, how excited he is. I think we should move. This is an example, but there's lots of kinds of to make a quantum computer, actually. There's not only one way of doing that. This is the introduction, but what have I done, right? Now I'm going to explain the part of Boolean games played in a triangle. So far, there will be no quantum. In this case, we have three players. We have Alice, Bob, and Carl. And all of them are given a binary input, coin, X represented by this yellow coin. X, Y, and Z is a number, either 0 or 1. And they must output another bit, which is 0 or 1 as well, A, B, and C, represented by this bronze coin over there. Then you take pairwise functions of the inputs, and you compute that function that will give you either 0 or 1. And you do the same with the outputs. They are given their input coins, and then they are separated. They cannot communicate during the game. The game will consist of, for instance, for the first game between Alice and Bob, they win if the input function of the inputs matches the output function of the outputs, like this. And they play the 3 games there. So the choice of your input and your output function defines the game that they'll be playing. For instance, again, the CHSS game consists of choosing for the input function the Boolean AND over there, and for the output is the XOR. So if they are playing the CHSS game, their winning conditions are those that you're seeing over there. And the inputs and the outputs, important, will be used for both, all of the games that they are playing. I said that the choice of I and O defines the game, and these are Boolean functions. Well, first, you can compute the players are playing the game, you can compute the average between the two games that they are playing, the probability of winning one game and the other. And the same for Bob and Carl. So here, to define the game, in principle, here are all the possible 16 Boolean functions, but only 10 depend explicitly or non-trivially on both variables, and that's what we like. So that means that for your input function, you can choose any of those 10, and for your output function, again, any of those 10. What this means is that, in principle, there will be 100 games to analyze. Now you go like this. But don't worry, because I classify all of them, and we only need 7. With 7, it's enough to analyze all of them because of the symmetries and all of this. So you can breathe, don't worry. Before I go with the quantum stuff, I need to explain my notation because we use a different one. I'll be using the bracket notation or the Dirac. So the ket is over there, which is your normal column vector. The bra is the row complex conjugate. With the bracket, then you form your inner product, and the ket and the bra, you do your outer product. And this is true. For us, a cat in a bra is that. For a non-physicist, is the other one. The basis for 2 qubits, it will be denoted like this. Okay? 2 quantum bits, so either 0 or 1, it will be denoted like that. And here are all of the other elements of your base. If you have more qubits, then same thing. Okay, so before there was no quantum, but now the quantum is that I'm giving the players 2 quantum coins each. So we have here, in principle, we'll have a 6-qubit state that will have, in general, 64 components, complex numbers. But I'll come back to specify this a bit later. Now let's imagine that I'm giving all of the players 2 qubits. What do they need that? Well, because they will perform a projective measurement to decide on the output bit. What does this mean? First, let's focus on Alice. Imagine that Alice gets as input x equal to 0. So she will have this projector there to decide when her output will be also 0. So that state is a projector and is defined like that. And it has a parameter. This parameter that is a free parameter between 0 and 1. Either Alice outputs 0 or outputs 1. So the projector for the output 1 would be the identity minus the previous projector. So lots of things. What the hell does this mean? Well, Alice is actually asking herself this question. Are my 2 qubits in this state, the quantum state? So she has these 2 qubits, and she chooses a state to compare with. If the answer to this question is yes, the output is 0. If the answer is no, the output coin is 1. That's why how they are using the quantum resource. And the choice of this number between 0 and 1 is determining which state you're choosing to compare with. When she gets input x equal to 1, in principle, she could pick another state to compare. Again, another number between 0 and 1. So at the end, what this means is that Alice's strategy is, for both inputs, is a choice of 2 numbers between 0 and 1. that are related to the state that she'll be comparing the two qubits with. This is what this projective measurement for the output bit means. The quantum is just a fancy way of computing that conditional probability. So the probability of A, B, and C, given that X, Y, and Z occur. So you're just computing that conditional probability according to the quantum recipe, if you like. When you have your conditional probability, you can compute the player's payoff, and then you do your stuff. This is the quantum state that they'll be using. And in those projectors are the strategies of the players, again, related to the state that they'll be comparing with, and numbers between 0 and 1. Now let's get back to the quantum state. The sandwich part, okay? At 2 qubits per player, 6 qubit quantum state. And there will be two possibilities of how to produce this state. So either I produce 3 qubits, then I produce another 3, and I give Alice will have these 2. Or I produce them pairwise. I produce this, this, and this. Alice's, Bob's, and Carl. These are the sandwiches, okay? So here I'm producing 2 identical sandwiches with 3 slices of bread, and with the other I'm producing 3 of 2. And I'm using the same amount of bread, if you like. For the tripartite sandwich, I'm going to call it a sandwich. It's not a sandwich, it's quantum state, okay? But it's easier. For the tripartite state, I'll be using a GAZ-like state, 2 of them. Okay? That will depend on, again, a parameter between 0 and 1. That number determines how much, or the amount of entanglement in your state. For the other sandwich, I'll be using a bell-like state. In this case, very similar, but we have 3. And again, we also have the parameter that controls the amount of entanglement there. So every time you think you are seeing the sandwiches, it's not fixed sandwich that I'm using. I'm using the entanglement parameter is telling you exactly which state you'll be using, but it will depend in general of these 2 numbers between 0 and 1. So that's everything so far. I've been talking for, I don't know, a lot. But so I'm gonna have an active break. I'm gonna ask you to guess this film. It's Matsy, if you like. What is this film? Mean Girls. You have the mean, the average, if you like. There's girls, Mean Girls, 2004. There is another one a few months ago. I watched it. It's the same, but they sing. I don't know if you like that, then just do it. You can watch it as well. Maybe you are super bored right now, but you're afraid to leave. So I'll give you a task so that you can ignore me for the rest of the presentation, which is which number comes after this sequence. You don't need a mathematical background to guess this. So feel free to just ignore me, yeah. Okay. Now I'm gonna do a summary of the setup because there are a lot of things were going on. First thing is you define your game. You choose 2 Boolean functions. Then you compute your conditional probability according to your quantum recipe. And you do it for both of the states. Then, once you have your conditional probability, you compute the player's payoff for all of them as the average between the 2 games that they are playing. Again, for both states. The player's payoffs will depend on these 6 numbers, which are the player strategies, okay, and are related remember, to the state that they will be comparing with. It will also depend on the amount of entanglements of your sandwiches, of your quantum states that you're using. So we have all of those variables there. And all of them are numbers between 0 and 1. Once you have your payoffs, you need to optimize them. For instance, looking at Alice, what you would like is you like to optimize her payoff by varying her own strategy. Her payoff will also depend on what Bob and Carla are doing and the entanglement in your state that you're using. But she can only change her own strategy. And those strategies are numbers between 0 and 1. You will do a similar problem for Bob and Carla. What you're doing there is you'll be computing the Nash equilibrium points. A Nash equilibrium is a set of strategies in which no player wants to unilaterally deviate from it. So in a sense, in those points, everyone is happy. If they move, they get worse. If you haven't watched it yet, the film, A Beautiful Mind, on the life of John Nash. It's amazing. After all of this setting, what did I want to research into, or what were my questions? First is I wanted to compute the new Nash equilibrium that they appear with the quantum resources and how we can compare them with the classical ones, not using any quantum. The second question was that do the players prefer to use bipartite or tripartite resources in this case? Bipartite resources are easier to produce. Tripartite, we are getting there experimentally, so which one would be better? So basically, I wanted to stage to fight over that setting playing Boolean games. Go back to the maximization problem. That's a convex optimization problem. You can use the software that you like, but I'm very much in love with Mathematica. It's very powerful for analytical computations. And I think I would marry Mathematica. I would have occasional love for Python, maybe. And MATLAB as a one-night stand, maybe. You can judge me, that's fine, but that's my choice. Some of the results, okay? This was all of the setting. First step was defining the game. Here are the possible choices. I'm gonna stick with my fetish game, maybe. Is this the HSH game, which means closer, Horn, Shimon, Holt, and it's based on an inequality in quantum mechanics from the late 60s. Very, very important. So this is the game that I will be showing you the results for. We'll be playing that game. Some results. For the tripartite sandwich, for the GHZ-like state. For you to see, this is Alice's payoff. That depends on lambda, your entanglement, your sandwich, and the player's strategies, numbers between 0 and 1. You optimize that, and you find your Nash equilibrium there. And those are the equilibrium points up to player permutations. If you compare them to the classical one, they are exactly the same as classical, without any quantum, using mixed strategy. You have the strategies, and they have associated some payoffs. Okay? And the payoffs depend on your entanglement parameter. You can plot them. For instance, here I'm plotting the blue dot and the red. So it corresponds to that. So as you can see, for the first strategy, regardless of how much entanglement, I'm plotting, sorry, the entanglement parameter, average payoff against your entanglement parameter of your sandwich. So regardless of how much entanglement you have, it doesn't matter. The payoff is constant. However, for the strategy in red, see that as you increment the entanglement. This would be the maximum entanglement, 1 over square root of 2. It increases the payoff, and then it decreases. So in this case, having more entanglement will help you to get more payoff for the players. Then there's more strategies. In this case, this will be a 2D plot, don't worry. Then for the other state, the bipartite sandwich, we have a lot of equilibrium points. Some are the same as the classical ones, but there are new ones. The first thing that you notice here is that some of the equilibrium points depend or are valid only in a certain interval of your entanglement parameter there. There are even strategies that depend explicitly on your entanglement parameter as well. Again, I can plot it. The squares match those lines, so it goes down and then it goes up, and for the red, it goes up as the entanglement increases and then goes down. More equilibrium points, there's a lot. First, let me tell you a bit about this strategy because I think it's very interesting. So this strategy, it depends on your entanglement parameter. Okay. That strategy, when there's no entanglement, when the lambda is 0 or 1, okay, you have no entanglement. That strategy evaluates to 1/2 for all of them. That's fine. The payoff associated is 0.5. That's fine. But this same strategy you get when you have 1 over square root of 2. And that for that value is the maximum entanglement that you can get for that sandwich. So you have the same strategy for 2 different values. What happens here with the payoff? Oh, the payoffs for the players are slightly higher, even though the strategy is the same. The payoff for the players is a bit higher than without entanglement. So if you tell me that I have this strategy, by just looking at how much the players are getting, I can tell you if there was entanglement or not. This is a bit related, well, not surprising. This is related to the field of self-testing. Self-testing aims at certifying that a process is quantum by just looking at correlations. Okay? If I give you a box and you don't want to open it or break it, how do you test that it does quantum stuff? So this is this field of self-testing. But there's much more work to do for that. I'm not sure. If we want to compare the THC scheme for both, here are the 2 plots. If we only care about the one that gives me a highest payoff, we could say the tripartite sandwich wins this battle. But the bipartite sandwich, so it loses. But there's many other games in which actually that one is better. And that's what I've done for my thesis. We're almost there. The take-home messages are, first, quantum games. It's a fancy way of computing conditional probabilities. Once you have your conditional probabilities, you compute your payoffs, and then you do your game theory, or you do whatever you need to do with them. Okay? Games with quantum stuff. Then the second message is that the triangle network is very interesting when you consider games and quantum resources. And that's what I've done. So almost there, but first I need to thank a lot of people. I've been here for more than 4 years. So here it goes. First, I need to thank my mom. She unfortunately couldn't make it because she got a surgery on Sunday. She's fine, but of course she couldn't travel. So, gracias, mama, si me estás bien. I don't know if she's connected. We'll see. Hopefully she is. And thanks also to all my family, of my father's side, of my mom's side, my brother, my sister-in-law, my 2 nephews, Mario and Alex, my cat there, his name is Rey, which means king in Spanish. You can imagine how he lives. Thanks also to my friends back in my village, but also in my university from my degree. And I would like to say a few words to acknowledge this man over here, Professor Vicente Jimenez Gomez. He was a professor in my degree, and he's basically the reason that I chose to do quantum. And he passed away a couple of years ago unexpectedly. So everyone was shocked and very sad about that. So I'd like to thank him because his passion, his love for quantum physics made me fall in love as well. So he's the reason I'm literally here. Then to all of the people I've met in Galway, this is a few days after I arrived. For me, coming is from Spain, late September. That day was a normal, even cold day. Little did I know, sun, amazing. I would like to thank all of my friends, all of the amazing people that I've met over the years here, Postgrad Society and all of the societies that, yeah, from attending all of those events, I met this amazing range of people. And yeah, there's many more. If you are here, but you're not in one of these pictures, either I don't have a picture with you or we're not friends that much. Take it as you like. Then also, thanks to my housemates over there, that was April 2020. In the lockdown, I tried to cook this Easter bread. It was terrible, but of course. Then we had my amazing housemates. We've had a lot of fun here, a few of the house parties that we've had. And then finally, I'd like to thank the university. No one from management, so yes. So management could be improved, but the people at the university are in general amazing. Also, thanks to the Researcher Development Center for all of the amazing workshops that they have provided for free. I've learned a lot. Thanks to the societies and the clubs, been to many, many events, and I've learned a lot. Finally, thanks to Michael over there, because he was very kind from the start, has never pressured me, he has guided me. Basically, he's allowed me to do whatever I want, project-wise and with my time. And I think that freedom was very important. Thanks to that, I think I've become an independent researcher, which sometimes might be not the case after the PhD. So, also, vielen Dank to Kirsten. I've been working there for more than 4 years. Before the pandemic, during the pandemic, when we had to do sums with email, you can imagine that. Then online, then back again. So I think the students and we, the tutors, are very lucky to have her as the manager. She's done an amazing job. Then thanks to Grazie, Angela, for being so kind and supportive and caring for us, so the Dean of Graduate Studies in our school. The administrative staff, you all know, all the PhDs that I met, the past and the present ones, and in general, all the lectures, all the staff. You know, you come from another country, you don't know anyone, and you're a PhD student, you're like, you don't know anything. And everyone was so kind, so nice, so supportive. And the respect that the people in this school show for the PhD students since day one is not something that is common. I've talked to many PhDs in these universities, in this university and in other universities, and that environment of supportiveness and respect is not as common as you might think. So well done, all of you. Again, I've learned a lot professionally over these more than 4 years, but more personally. And that's, you can ask my family. I wasn't as nice, as social, and all of this before coming here. It's true, you can ask them. So that's because the environment has allowed me to be like this. So thank you to everyone. That'll be it. But here comes what's next then? Say it. The joke. Yes, Koshi, thanks. Final joke. There are two jokes. There's two jokes. One in English that I will read and one in Spanish so that they can understand. What did the PhD student say when they solved a complex equation? That's what I call a masterpiece. No, el otro es para vosotros. Okay, maybe it's not. It didn't translate well, so I had to find another one. Anyway, so that's all for me. So I'll happily take any questions that you might have. Thank you. Yeah, got it.
Have you computed the players? Everyone wins. One example that the payoff for each of the three was 0.5.
Yeah, you're averaging between the two games, and then the maximum is 1.
So they don't have all those.
Oh yeah, no, it's fine. No, they might win one game.
No, but then they get the 0.56 each.
Yes.
Which is more than.
But the maximum for each player is 1.
Yeah.
You compute the payoffs separately, and each payoff, the maximum is not that you add them, and it should be cut by 3 if you want. Makes sense a bit? Sorry? Yeah, exactly. Exactly. Yes. Yeah. Sorry. So they win together. Every time they win together that game. But maybe you win this game and then you lose the other game. So that's on average. Yeah. It depends on the game that you have to find. Yes. Yeah. No, that's fine.
What happens if you?
Yeah. Yeah. So the easiest way would be, well, you could consider, let's say that I was considering, like, you could consider the full range with even complex numbers and all of this. But even sometimes all of the states can be transformed continuously into that one. But I'm not really sure how that would affect, or maybe there are other higher dimensional states that give you better or something like this. Yeah, let's see.
Okay, so you can start again for a couple of stuff.
Wait,
That's a course, sorry.